In our final video in our series on Lewis structures, we're going to investigate how to draw the Lewis structures of covalent compounds that actually have charge. If this sounds familiar, that's because we're going to learn how to draw polyatomic ions. Now, the good news is that pretty much all of the steps from the previous video also apply to polyatomic ions, although because of the fact that they have charge, they come with a few extra steps, starting right at the very beginning when we draw the structures of each of the atoms within the compound and count the total number of valence electrons. And this is because the total compound has charge, meaning that if it is negatively charged, this compound means that it has gained electrons compared to the neutral atoms. And if this polyatomic ion had positive charge, that would mean that it has lost electrons compared to the individual atoms. This is easier to understand when we actually go through the procedure of doing this. So if we remember the Lewis structures of carbon and oxygen respectively, we know that carbon has 4 valence electrons and we only have 1 carbon atom, so that's nice and easy. Oxygen, however, is going to have 6 valence electrons, and because there are 3 oxygens in carbonate, we multiply that number by 3 for a total of 18 electrons. Now here is the first major difference. Carbonate is a polyatomic ion that has 2 electrons, or rather it has a -2 charge, meaning that it has gained 2 electrons, which we need to incorporate into the total number of electrons, otherwise our structure would not be accurate. So 4 plus 2 is 6 plus 18 brings us to a total of 24 electrons that we can use. Now, before we jump in and draw the structure, let's do a quick review of identifying whether our compound is an ionic or covalent compound, because this gets confusing for some people, because even though carbon and oxygen are both nonmetals, it has charge. So what kind of compound exactly is this? Well, if we measure the electronegativity of carbon and oxygen, 2.6 and 3.4, we can do a difference of electronegativity and average of electronegativity calculation quickly here. So 3.4 is oxygens and 2.6 is carbon. So if we do some quick subtraction here, we see that the difference comes to 0.8. And then if we take the average electronegativity, or the mean electronegativity, we see 3.4 plus 2.6 comes to exactly 6.0, and 6.0 divided by 3 means that our average electronegativity is going to be 3.0. So if we remember these numbers, we can check our triangle of bonding. Let's just make some space here for clear comparison. And we have 0.8 is our difference in electronegativity, and 3.0 is our average. So the convergence point would be about here, meaning that we, although it's a little bit ambiguous about whether this is polar or non-polar covalent, it is definitely a covalent bond. So that means that we can draw the Lewis structure as normal, and we will explain how to deal with the charge at the end. So because of the fact that carbon has 4 unpaired electrons, we're going to put it in the center of our molecule, or in the center of our structure, because it has more unpaired electrons than oxygen does. So oxygens we position around it like so. Then we can connect each of the oxygens to the carbons with single bonds, and if we're keeping an electron total, that means 2, 4, 6 electrons are what we just used, meaning that we have, if we do some quick math here, which I swear I know how to do, we see that we have 18 electrons remaining. Now, then, before we add on any multiple bonds, double or triple bonds, we can put the lone pairs back on oxygen. So that's exactly what we're going to do here. We're going to add 2 lone pairs, meaning 4 electrons to each of the oxygens, which brings us, or which means that we have just added 12 electrons to oxygen, meaning that there are a total of 6 electrons that remain. Now, at this point, If we were to follow our step-by-step guide on drawing Lewis structures, we would add in double bonds, and lo and behold, there's 1, 2, 3, and that's all of the electrons that we have added. But of course, we have a problem. If we count the number of bonds this carbon has, we see that the central atom carbon has 6 bonds, meaning that it has 12 valence electrons instead of 8, and that is not physically possible, which means that, let me just erase 2 of the double bonds here. Once we add the first double bond here, meaning that we've added 2, meaning that we still have 4 electrons remain, our carbon in the center already has a full 8 valence electrons, meaning it has a full octet, which means that we can't actually add any more electrons, so our procedure for drawing Lewis structures needs a bit of a rework. But remember that this molecule has charge. So instead of adding bonds, which is not possible to do, what if we take those 4 electrons and add on 2 more lone pairs like this? That means that we have just used all of our electrons, so we don't have any electrons remaining. And if we just count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 is the total that we should have, including the 2 extra electrons from charge. And if we count to see if all of our elements have a full octet, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, it looks like all of our elements have full valence shells, which means that our structure is mostly done. Now, here is where we factor in the fact that we're drawing an ion. So because ions have charge, we would actually need to show that this molecule has charge, meaning that we need to add square brackets the same way that we would when we were drawing an ionic compound, only because the -2 charge applies to the whole structure. We would put the brackets around like this, and then just put the charge of -2 up here, and that would be our complete structure. Now, in addition to checking the number of valence electrons and making sure that each element doesn't have too many or too few electrons, but that they all have their full valence shell, the other thing that we need to check is identifying where the negative charges are, because here we can see that carbonate has a -2 charge, meaning that it has gained 2 electrons. And we know that electrons are naturally attracted to elements with the highest electronegativity. So the first thing that we need to identify is, well, where is the negative charge? And secondly, we need to identify if that negative charge is located on the element that has the highest electronegativity, meaning in this case oxygen, because electronegativity measures how well an element can gain electrons. And we can test both of these by calculating something that we call formal charge. Now, formal charge is a little bit of a misnomer because formal charge doesn't officially exist. Not really, anyway. Formal charge represents the charge, in quotes, of a specific atom when this is actually part of a compound. Now, because of the fact that this is covalently constructed, the fact that all of these electrons are shared, means that formal charge doesn't really exist, but more accurately is a measurement of whether the atom in question has either gained electrons or lost electrons when it is bonding to the other atoms that it is bonded to. And the way that we calculate formal charge is relatively simple. We start with the starting number of valence electrons, which in the case of oxygen is going to be 6. So let's do this with carbon dioxide as an easier molecule here. So here we're calculating the formal charge of oxygen here. So oxygen, neutral oxygen as an atom, starts with 6 valence electrons, and then from there we subtract all what we call non-bonding electrons, which sounds a little bit confusing, but remember that electrons in a Lewis structure can either be bonding electrons, meaning that they are shared, or they can be lone pair electrons, which belong only to one element. And this oxygen in carbon dioxide each have 4 non-bonding electrons, 2 in this lone pair and 2 in this lone pair, and likewise on the same oxygen, because in terms of electrons, it is identical. Finally, we then subtract from that 1 electron per bond that atom is making. And the reason why we say 1 electron per bond is because each of these bonds is a covalent bond, meaning that half the electrons effectively belong to oxygen and the other half of the electrons belong to carbon because they are shared. So the oxygens bonded to this carbon have 2 bonds, which means that there is 1 electron for each bond, meaning 2, and 6 minus 4 minus 2 is 0, so that states that this oxygen here has a formal charge of 0, meaning that it has neither gained nor lost electrons compared to the atomic form. It has the same number of electrons as it started with. Now, if we do this with carbon, the calculation is actually even easier because carbon starts with 4 valence electrons that we see here. It does not have any lone pair electrons because carbon only has unpaired electrons, and we can see 1, 2, 3, 4 bonds with carbon. 4 minus 0 minus 4 is 0, meaning that the carbon here is also neutral. So, now that we have a way or a method to calculate where charge is within a molecule, now we can actually try this with our structure of CO3 2-, our structure of the polyatomic ion carbonate, which I am quickly redrawing here for the ease of comparison. Now, a few things that we use formal charge for. Elements are always stable as long as their formal charge is as close to 0, meaning as close to neutral as possible, meaning that the element has neither gained nor lost electrons. Now, this is not possible in our case because the total formal charge of every atom in the structure is equal to the total charge of the actual compound itself, which means that we should find a formal charge of -2 in total in carbonate, meaning that if there is negative formal charge, it will always be placed on the element that has the highest electronegativity because this represents the element that is best at gaining electrons. So if we do some quick calculations here, oxygen starts with 6 valence electrons. There are 4 non-bonding lone pair electrons and 2 bonds, which means that this oxygen here has a formal charge of 0, so we're good. The carbon in the middle, carbon starts with 4 valence electrons. There are no lone pairs in the structure, and 1, 2, 3, 4 bonds. So 4 minus 0 minus 4 is a formal charge of 0, so we are good as well. And these 2 oxygens down here, we can do one calculation because they are identical. We have 2, 4, 6 lone pair electrons and 1 bond on each of them. So oxygen starts with 6 valence electrons. There are 6 non-bonding electrons on each oxygen and 1 bond for each of them, which brings each oxygen's formal charge to -1. Now, if we have a -1 charge here and a -1 charge here, -1 plus -1 is -2, so the total formal charge matches the total charge of the polyatomic ion, so we are good. And because oxygen has a much higher electronegativity than carbon, we also have placed the negative formal charge on the element with the highest electronegativity, so we know that our polyatomic ion has this successful structure. To practice this ability to draw compounds that have charge, as well as get some formal charge practice, you can take a look at the following polyatomic ions below and see if you can use these examples to practice not just how to draw a covalent compound that has charge, but also make sure that the charge is located in the right part of the molecule.